So good day, and this is my demo video for task 2 in our hands-on lab number 6. So task 2 states that design a circuit that can be built using a NAND gate only that will output logic 1 whenever the 4-bit hexadecimal is an even number from 2 to 10. Use the information above to create a truth table, draw the K-map from the truth table data, and draw the design circuit using NAND gates only. So the first thing I did in this task was to identify what are the even numbers that we will be using, the 4-bit hexadecimal even numbers. So here I'll show my solution first. As you can see, I identified what even values. So we have the even numbers 2, 4, 6, 8, and 10. So in hexadecimal, they are these corresponding values, and I converted it into the 4-bit binary equivalent. For 2 it is 0010, for 4 it is 0100, 6 is 0110, 8 1000, and for 10 we have 1010. So that's my first step in solving this task. Next is use the information above to create a truth table. So going back to my truth table over here, I have the 4-bit binary combinations. So the output of the even numbers here must be at logic 1. So we have 16 outputs from 0 to 15, 16. So the even numbers must, their x must correspond to logic 1. So we have here at 2, at 2 is 0010, 0010. The output is logic 1. At 4, 0100, the output is logic 1. At the next, for the 6, 0110, the output is logic 1. For 8, it's 1000, the output is logic 1. For 10, it's 1010, the output is also at logic 1. So as you can see, from the based on the even numbers assigned, I have created this truth table. So my next step was to draw the K-map from the truth table data. So using the truth table, I based on one of the topics, the handouts. So this, given the truth table, finding the logic 1, and then find the correspond m variable, so that that will be the logic 1 and our K-map. So going back to my truth table, we have here m2, right? So it's a complement, b complement, c for logic 1, and d complement 0. So moving on to m4, which corresponds to the fourth, to even number 4, we have a complement, b is correspond to 1, c complement, d complement, also 0, it's 0. So for 6, we have m6, which corresponds to a complement, b, c, and d complement. So for 8, it's a, and then followed by b complement, c complement, d complement. For m10, it's a complement, a, b complement, c, and d complement. So as you can see, I have here my corresponding even numbers and their combinations to be used for our K-map, which I based on the handouts. So our next step was to draw the K-map from the truth table data. So I'm gonna show my K-map here. As you can see, I'll just zoom it a little bit. So we have our K-map with the respective variables. So I based the formation of this K-map in these handouts. Let me just check here. These are the numbers that where we will put where the M corresponds. So I've just followed this orientation to this K map I drew here. So we have first for 2, right? It's M2, it's here. M4 for 4, 6, M6 is here. M8 is here, and M10 is here, which corresponds to the this arrangement that I based on. So, and then I now went to into grouping the ones. So as you can see, there are only 6 logic ones. I'm first gonna group this group in M2 and M6, so it will give this combination: A complement for their horizontal and C D complement for their vertical uh, common terms. So I'm gonna move on. This next two is M8. Next group is M8 and M10. I'm gonna group this together by 2. So the output, the common terms for the horizontal is A B complement. For the vertical, it's D complement. So we have A B D complement. And lastly, the solo group of 1, it's gonna have a combination of A complement, B, C complement, D complement. So adding this all together will yield to A B complement, D complement, it's here, plus A complement, B, C complement, D complement here, and A complement, C, D complement here. So this is my simplified equation in which I will base on my circuit to be designed, in which I will show in a while. So using this simplified circuit, I will go first to my logically, because my this is where I base this is where the Tinkercad design will be based later on. So this is my simplified equation, right? And using this logically, I will prove that this I configuration I made using the NAND gates. I use the NAND gates, universal NAND gates, their respective configurations. So as you can see, there are all NAND gates, the and the OR. I use the AND, the OR configurations. So I'm gonna show that my design is working properly. So let's first test for, let's go back to the binary equivalent of 2. It's 0, it's here, A complement, B complement, C, and D complement. So C is only at logic 1. So let's see. So the output is at logic 1. So turn it off. I'll go back. Next is M for the 4. For M4, A complement, B, C complement, D complement. So B is only turned on. B is logic 1. The rest are logic 0. So the LED is at logic 1. Next is for 6, it's A complement, B, C, and D complement. So B and C are turned on. B and C are turned on. So as you can see, the LED, the output is still at logic 1. So next is for 8, it's A, B complement, C complement, D complement. Only A is turned on. So I'm gonna go back here. As you can see, turn on A only. The output is a logic 1. And lastly, for 10, it's A, B complement, C, and D complement. So A and C must be turned on. A and C. As you can see, the uh, output is still at logic 1. So I'll move on to my last, draw the design circuit using NAND gates only. So after showing my logically, this is where I based my Tinkercad design. So this is my Tinkercad design. I'll start the simulation, So as you can see, I just used the 6 NAND gates. There are different configurations. First, I have a quad NAND gate, triple 3 input, and dual 4 input, because I have 4 input back in my logically. So I just use different configurations of only NAND gates. So by configuring and connecting the circuit, I have come up with this design. So I'll start the simulation. Let's go back first. M2 is A complement, B complement, C, D complement. C is only turned on. So going back, C is turned on. As you can see, the output is at logic 1. I'll turn it off. For 4, it's A complement, B, C complement, D complement. Only B is turned on. Only B is at logic 1. So let's see. Here is B. I'm turning it on. The LED is at logic 1. The output is logic 1. So I'll go back. For 6, it's A complement, B, C, D complement. B and C are only turned on. B and C. So as you can see, the LED is still at logic 1. Turn it. I'm going for the next is M. For 8, it's A, B complement, C complement, D complement. Only A is turned on. So I'm going to show A. A is at logic 1. The LED is at logic 1. So next is for M10, A, B complement, C, and D complement. So I'm going to turn on AC. So this is the output still at logic 1. So with this design, I have met the requirements for task 2. And that's it. Thank you for watching.